Hello everybody, this is Homer White back again with the first part of the 9th chapter of our course on confidence intervals. In this part of the course, we'll get the general idea of confidence intervals as compared to the probability computations that we've been doing recently. And we'll also learn about confidence intervals for 3 of the basic 5 parameters, the parameters that involve means. Always remember to make sure that the necessary packages are loaded. First of all, let's talk about that transition from doing probability to doing statistical inference, and in particular, to being confident about things. Say that you're about to flip a fair coin. Think about what happens before the flip. Before the flip, you know that chance will be at play. That coin could turn out to be either heads or tails, and you don't know what it's going to turn out to be yet. But you do know, by the fairness of the coin, that the probability of heads is 50%. Say you've already flipped the coin, and now it's hidden in your hand. It's either heads or it's tails, but there are no chances left about it. However, before the coin was flipped, it had a 50% chance to be heads, and you know that. So on that basis, you are now 50% confident that it is heads. We all have a notion of confidence, and this notion of confidence is often based upon our knowledge about probability of the random process that has already occurred. It works the same way when you're taking a sample from a population. Say you're about to take a simple random sample of big enough size N from some population. We know some probability theory. The 68-95 rule for probability says that there's going to be about a 95% chance that the sample mean x bar will turn out to be within 2 standard deviations of x bar from mu, the population mean. Now, if you think about this, you could reword that. You could say there's about a 95% chance that mu will lie within 2 standard deviations of where the x bar turns out to be. After all, for x bar to be within 2 standard deviations of mu means the same thing as for mu to be within 2 standard deviations of x. After you've taken the sample, there are no chances left. Mu either lies within 2 standard deviations of x bar, or it does not. But because of your knowledge of the probability, you are now about 95% confident that mu lies within 2 standard deviations of the x bar that you actually got. It's just like the coin flip situation, except this time we're dealing with something that had a 95% chance of happening, and on that basis, we're now 95% confident that it did happen. Now, we want to go out on a limb here just a little bit. In that statement about confidence, I'm going to replace the standard deviation of x bar with the standard error of x bar. So what I'm going to say is really not right, but I'm hoping it's approximately or roughly right. I'd like to say that I'm about 95% confident that mu lies within 2 standard errors of the x bar that we got. As we know from the very last part of Chapter 8, this is part of the 68-95 rule for estimation. Now let's talk about how R actually computes confidence intervals. It doesn't really use the 68-95 rule for estimation as we do. First, we'll deal with intervals for one mean. Remember the Math 111 survey data, and remember that one of the variables measured on the students was the fastest speed that you'd driven ever in your life in miles per hour. Let's go ahead and define the population parameter mu, the mean fastest speed ever driven for all Georgetown College students, not just the 71 that got into the survey. And let's say we've got a research question. Say we're wondering, on average, how fast do Georgetown College students drive when they drive their fastest? Notice that because the parameter of interest is mu, this question is actually just equivalent to what is mu? Now a confidence interval for mu is going to give us a range of reasonable values for mu based on the data at hand. Let's go ahead and one more time compute a confidence interval for mu using that 68-95 rule for estimation. And then we'll turn to the ways that R makes these intervals. So we're going for a rough 95% confidence interval for mu. Well, we are about 95% confident that mu lies within 2 standard errors of x. That's the 68-95 rule. So we just need to get x bar and the standard error for x bar in order to actually make that interval. Phase stats will help us out here. So if we take phase stats on fastest speed ever driven, we find that the mean for the sample is 105.9 miles per hour. That's our x bar. We also find the standard deviation for the sample, 20.88, and the sample size, 71. The standard deviation for the sample and the sample size help us to compute the standard error for x bar. I'll go ahead and use R like a calculator to get that standard error. So 20.87 was roughly what it was. Divide by the square root of 71 and put it into something named standard error and print it out. So it's about 2.478. But now let's go for the actual rough 95% confidence interval. For that, using the 68-95 rule, we're going to need to subtract and add 2 of those standard errors from the sample mean. So we try the sample mean minus 2 standard errors. That turns out to be 100.9. We compute the sample mean plus 2 of those standard errors. That's 110.9 miles per hour. Those 2 numbers give us the lower bound and the upper bound for our rough 95% confidence interval. It's always good to interpret your confidence interval to people who might not be as familiar with statistics as you are. So you could say something like this. We're about 95% confident that the mean fastest speed for all Georgetown College students is somewhere between 100.9 and 110.9 miles per hour. And so you state your lower and upper bounds, and you use some units along with it. And you state your level of confidence. Once you have your interval, which is a range of reasonable values for what mu could be, based on the data you have at hand, then you can answer all sorts of questions that people might have about the value of mu. So let's think about this one. Would it be reasonable for someone to believe, in the face of this data that we have, that mu is just 100 miles per hour? Well, I think no, and here's why. For one thing, the confidence interval is supposed to be the range of values for mu that are reasonable based on this data. But also, 100 lies outside of this interval. It lies beneath it. So that rules 100 out. It's not impossible that mu is 100 miles per hour. Maybe we just had a rather unlucky sample with some rather high speeds in it. But it seems unreasonable or unlikely that we might have had such a large sample, at least if we think in terms of the confidence interval. And what we'd like to do mostly in this chapter is to take a look at how R does things. We want to move away from our rough 68-95 confidence intervals to intervals that have much closer to the desired or advertised level of confidence that we attach to them. And for this, we can use a function called t-test GC. You might be wondering, what does that name mean? What's the T? What's test? Aren't we asking for confidence intervals? Well, we'll get to all of that later, but for now, let's just learn how to use this function. The code is pretty simple, so you might want to give this a try yourself if you have R open. Run t-test GC, twiddles fastest, data is the Math 111 survey. Notice the familiar formula data input. we're interested in one numerical variable here, the fastest speed, and so we have our typical form for the formula, twiddles and the numerical variable we're interested in. And of course, as always, we tell R what data frame we're going to find that variable in. Here's a little tour of the output that you get. First of all, R backs you up, and instead of going straight for the confidence interval, gives you some descriptive results. So it simply tells you the x bar, 105.9 miles per hour, the standard deviation of the sample speeds, and also the sample size. We'll see later why this is so important. But then R moves to inferential types of results. So now it's thinking, what could we say about the population mean based upon the sample data that we have? Well, x bar is our estimator for mu, and so R reports that our best estimate for mu at this point is 105.9 miles per hour, and it gives the standard error for this estimator, the 2.478 miles per hour. Then it goes on to the confidence interval. You'll notice that it's not quite the same as the confidence interval that we got from the 68-95 rule. It differs by about a decimal place. Now, there are other confidence levels. For example, the 68-95 rule talked about 68% confidence intervals, 95% confidence intervals, and 99.7% confidence intervals. But really, you can go for any level of confidence between 0 and 100%. All you have to do is state that confidence level to R using an extra argument called conf.level. You specify the level as a proportion rather than as a percent. So if you wanted, for example, a 90% confidence interval, then say to R that conf.level should be 0.90. When you run this code, you get the same descriptive information, but when it comes to the confidence interval, you find that it's a little bit narrower now. The interval is narrower, but on the other hand, we're only 90% confident this time, as opposed to 95% confident that mu really lies inside of this interval. Keep this in mind. The confidence level that you desire is one of the things that determines the width of the confidence interval that you get. Lower levels of confidence give you more precise intervals, intervals that are narrower, but on the other hand, you're going to be less confident that mu lies inside of those intervals. The most common level of confidence that people ask for is 95%. We need to think more about what 95% confidence means, or what confidence means at any level, really. For this discussion, let's stick with 95% confident. Here is what it means. If you sample repeatedly from a population, and say you make a 95% confidence interval each time based on the sample that you get, then you'll get a lot of intervals. But about 95% of the time, mu will lie inside the interval you get, and about 5% of the time, it won't. To put it another way, 95% confidence intervals are designed to be wrong 5% of the time. This may sound a little surprising. Don't we want to be right all of the time? First of all, let's see if this really is happening. Let's try this little app that will give us an idea of how often a confidence interval at a given level of confidence fails to contain the parameter that it's trying to estimate. When you get the app running, in the plot window, you see a density curve for the heights of all of the people in our familiar ImagePop population. The red vertical line in the middle is the mean height for all the people in the population. So it represents the actual location of mu. Looking at the wheel, we see that we could take some samples from this population, and we get to choose the sample size, and we also get to choose the confidence level. We also can take one sample at a time, or we can take a lot of them at a time. Let's stick with our small sample size of 5, and the confidence level of 95%, and take one sample at a time by clicking on one of these sliders, but we'll try to keep the sample size at 5. With such a small sample size, you're not going to get very pretty histograms, but you do get one, a histogram for the 5 sampled items. You also get a confidence interval in yellow along the bottom, and the blue dot in the middle is the sample mean. Notice that this time the sample mean was fairly near the population mean mu, and the 95% confidence interval covered that mean. It was a successful interval. If you look over in the console, you'll see that R is keeping track of whether or not that interval contained the population mean. Let's try it again. And again. And again. So far, all of our intervals, and we've taken 18 of them by now, have contained the sample mean. They've all been successful. But I claim that about 5% of the time, that's about 1 out of every 20 times, the interval won't contain the mean. If I keep going long enough, I should see this happen. Wow. I had to go 60 times until I came upon an instance where my confidence interval did not contain the mean. Am I wrong about the probability? Probably not. But I really ought to try lots and lots of times in order to find a better estimate of the true chance that my confidence interval will not contain the mean. So tell you what, let's go ahead and take 1,000 samples at one time. We're not going to see each and every individual confidence interval in the plot window, but we can go over to the console and take a look at the number of times and the proportion of times that the confidence interval missed the mean. And I see that out of all the times it's tried so far, which is about 1,060 times, the confidence interval covered the mean most of the time, but missed sometimes. And the number of misses divided by the number of tries so far is about 4.52%. That's pretty close to the 5% that I'm advertising. If we could keep on taking 1,000 samples at a time and adding to our information, then we would find that the actual proportion of misses gets closer and closer to 5%. This works for any level of confidence. If I were to set my confidence to be somewhat low, how about 60%? And I'll go ahead and take one interval at a time. I find that we get very narrow intervals, but those intervals only have a 60% chance of covering the mean, so they should miss a lot. Let's see, that one missed. And this one missed too. If we do a whole lot of them at one time, we should find that about 60% of them cover the mean and about 40% miss. Let's see if that happened. Sure enough, we came close to those figures. It doesn't really matter the sample size. As long as the underlying population is normal, then we should get the advertised percentage of misses and covers. Let's increase the sample size just to see. Sample size up to 50. Let's try another 1,000. Another 1,000. Yep, sure enough, about 40% misses. Now that was just an app. We were pretending to know what the population is and pretending that we had the time to take lots and lots of samples out of it. In real life, you take just one sample. So you're going to get to make just one confidence interval, a 95% confidence interval, maybe. You're not going to know if mu lies inside that interval or not. But because of the probability theory that we have learned, our knowledge about how confidence intervals work so far, we can be 95% confident that that one interval that we do have does contain the mean. When you're just starting out making confidence intervals, it's good to organize your thinking and to organize the argument that you are going to make on the basis of that confidence interval. So I suggest a 4-step procedure to follow. First of all, define the parameter of interest that stems from your research question. Secondly, run the code, the t-test GC, and perform what we call a safety check. I'll talk more about that in a bit. Then report the confidence interval and interpret it. And finally, use that interval to answer the original research question. In the examples that we give in the rest of this presentation, we'll try to follow this 4-step procedure. About those safety checks, what are they and why are they important? Again, I'm going to have to hold off a little bit on the why until a later presentation. But I'll let you know right now that for every type of confidence interval you make, the safety checks are the same as the criteria for the central limit theorem to hold. So for confidence intervals for one population mean, the safety checks are going to be just the same as the criteria for a sample mean to have approximately a normal distribution. Recall then what they were. First of all, you need to be taking a random sample from your population. And secondly, the sample size n had to be big enough. Bigger than or equal 30 was the suggested cutoff. So, if your sample size is less than 30, you're going to want to check the graph of your sample for outliers or strong skewness. And if you don't see these, you're probably okay. If you do see them, you should be worried about the reliability of your confidence interval. The smaller your sample sizes, the more a given amount of skewness or a given outlier should worry you. Again, we'll learn why you do exactly this kind of check in a later presentation. For now, we'll just practice doing it. Let's move on to confidence intervals for the difference of two population means. Say we've got this research question. Who drives faster on average, Georgetown College males or Georgetown College females? Well, step 1 of the 4-step process that we're suggesting is to define our parameters that stem from the research question. We're evidently interested in two population means this time. Let's let mu1 be the mean fastest speed for all Georgetown College males, and mu2 be the mean fastest speed for all Georgetown College females. Since we're interested in whether or not males and females drive equally fast on average, we're really interested in the difference between mu1 minus mu2, and so we'll make a confidence interval for mu1 minus mu2. Step 2 was to run the code and do a safety check. First, let's run the code. So we'll go to t-test.gc, but this time, because we're studying the relationship between a numerical variable and the factor variable sex, we're going to have a formula that looks like numerical twiddles the factor variable. Also, we have defined two populations, the male population and the female population, and mu1 was the mean for the male population. Since we put the male population first when we were defining parameters, we want to make sure that R treats the male group as the first group. The argument first takes care of that. Once you've run the code, it's time to do your safety check. Again, safety checks have criteria that are always the same as for the central limit theorem to hold. So, for the difference of two sample means, remember that the criteria were as follows. You need to have taken two independent simple random samples from your two populations. It's also okay if you did a completely randomized experiment that has two treatment groups. Also, both sample sizes need to be at least 30. If they're not, then make graphs of the samples and watch for outliers and strong skewness. So how's it turning out for us? Are we safe? This is where the descriptive results come in really handy, and it's why they're included in the output. From the descriptive results, we can see that our sample size for the males was 31, and our sample size for the females was 40. Both of those sample sizes are big enough. Since we're also thinking that the Math 111 survey was like a random sample from the Georgetown College population, we can think of the sample of males and the samples of females as two independent simple random samples from the respective populations. So we're safe. However, if the sample size had been smaller, then it would have been a really good idea to graph those two samples and check them for the skewness and the outliers. Let's go ahead and practice doing this. I suggest using parallel box plots when you've got to look at two samples at once. So going back to Chapter 2, we remind ourselves that we can make parallel box plots with the BW plot function. Just use the formula fastest twiddle sex to get the two box plots in one window. And here's some extra arguments to give you nice, pretty output. If you run this code, you get this picture. Let's see what we've got. For the female population, I see an outlier. Also, I see a little bit of left skewness. Notice that the lower tail, the lower whisker, is shorter than the upper tail, the upper whisker. For the males, I see a couple of outliers, and perhaps a slight hint of right skewness. If the sample size had been quite small, I would have been pretty concerned about those outliers. Maybe a little bit concerned about the skewness for the females. But again, remember, our sample sizes were big enough, so we were good to go. Step 3 of the suggested process is to report your confidence interval. If you've run the code and you're showing it to the reader, then you're in good shape. You can just tell them to look in the output. This time our confidence interval went from 3.54 miles per hour to about 23.25 miles per hour. We think that mu1 minus mu2 lies somewhere in between those two speeds. You want to interpret this interval for your reader. Since you've defined mu1 and mu2 earlier on in step 1, you can use them in the interpretation. You can say something like, based on the data at hand, we're 95% confident that mu1 minus mu2 is somewhere between the 3.55 and the 23.25 miles per hour. Finally, you want to use your interval to answer the original research question. Recall that question was, do Georgetown College guys and Georgetown College gals drive equally fast on average, or not? Well, if both populations drove equally fast on average, then mu1 would equal mu2. And then mu1 minus mu2 would have to be 0. But our confidence interval went from about 3.5 to 23.25. That interval lies entirely above 0. Since that interval is supposed to be the range of reasonable values for mu1 minus mu2, then we can say that 0 is not a reasonable value. We can kind of rule it out. So we can conclude that we're pretty sure that Georgetown College guys drive faster than Georgetown College girls on average. Let's try the mean of differences. For this, let's use the labels experiment. Remember the research question from this experiment. Are people going to rate peanut butter more highly on average if it comes with a Jif jar than if it comes in a great value jar? Remember that in this experiment, it wasn't a taste test. People were actually tasting the very same peanut butter, just in jars that had different labels. For step 1, we need to define the parameter of interest. It's going to be a mean of differences. Let's let mu d be the mean difference in rating, GIF minus great value, for all Georgetown College students. And we'll make a 95% confidence interval for mu d. For step 2, code and safety check, we first run the code. Since we're dealing with paired data, we're going to have a slightly different type of formula. It's always of the form twiddles, and then the first numerical variable minus that second numerical variable that you're subtracting off from it. So for us this time, it's going to be twiddles GIF rating minus the great value rating. Also in step 2, we do a safety check. The criteria are the same as for the central limit theorem to hold. We need to have taken a simple random sample from the population, and we'll hope that the people who did the experiment did that. Also, the sample size should be at least 30. If it isn't, we'll check a graph of the sample for skewness and outliers. Well, the sample size this time is 30, but again, for practice, let's go ahead and check that sample for signs of the skewness and outliers. This time we've only got one sample. You could make a box plot of the sample. You could make a histogram of the sample. Let's make a histogram this time. Well, the sample is sample differences. We have the GIF ratings and we have the great value ratings in the data frame. But we should also compute the differences. So this is done in the line of code you see right here. So labels $GIF rating isolates the GIF ratings for R. Labels $great value rating isolates the great value ratings. And all in one line on your console, you would subtract the two. And then you should store the results in something with a good name. How about diff? Once you've done that, you can ask for phase stats on diff. You don't need to specify data frame. Diff doesn't come from a data frame. It's inside your global environment now that you've created that variable. We looked at phase stats so that we can get an idea of what is the minimum and what is the maximum of the difference in the ratings. The rating differences went from -5 to +8. This helps us to make a really good histogram for the differences. When we ask for the histogram, we give our usual labels for the axes and a good title. We could specify the breaks in the histogram. The specification that you see here allows each rectangle in the histogram to be centered over one of the possible values for difference of ratings. You certainly are not required to make histograms this fancy when you're just checking for skewness and outliers, but I thought you'd like to have a look at it. Here's the histogram that you get. As you can see, there's some evidence of either left skewness or possibly an outlier in this corner of the plot. So if this had been a much smaller sample, I would be somewhat concerned. It really is a judgment call, you know. We do see some left skewness, and maybe an outlier or two with smaller values. Also remember that our data here are integer values. They're not actually the product of a continuous random variable. So there could be some problems here. But at smaller sample sizes, at sample size 30, we're probably just fine. Before we proceed to the next step in the confidence interval process, we should just take a little time out and look at the estimate and the standard error that appear in the output. This time the estimate for our parameter is the d bar, and it turned out to be 2.367. The standard error for d bar is 0.513. Notice that if labels make no difference, then mu d would be 0. We have results that are about 4 standard errors above 0. So already intuitively, without looking at confidence intervals, we know that labels probably do make a difference on average. Results that are 4 standard errors away from a particular value are really unlikely if that particular value is true for the population. Now on to step 3 of the formal process. We report the confidence interval straight from the output of the function, and we interpret it for our readers. So this time we could say that we're 95% confident that the mean difference in ratings for all Georgetown College students, if they all could have been in this experiment, not just the 30 that we had, is somewhere between 1.3 and 3.4 points. Step 4, the conclusion, we use the interval to answer the original research question. Well, the original research question was whether people were affected on average by the labels on the jars. If the label had made no difference on average for the whole population, then mu d would be 0. But our interval lies above 0. So we're pretty sure that Georgetown College students would rate Jif labeled peanut butter more highly than they rate Great Value labeled peanut butter. Sorry, that should be a GV and not a GC. One small note, with confidence intervals in t-test GC, sometimes you just want the confidence interval and you don't need all the extra output. If you're ever in that situation, just set the argument verbose to false. So running code like this would give you just the confidence interval. Thank you for listening.